Hi guys, we are going to move along on inclines. The other day we went over an object at rest on the incline and we'll review some of those things because they're all going to be present for the most part here on sliding on the incline. And we're going to just jump right into an example. So this is example 6 on page 134 to have your books open to. And it's a situation of a skier sliding down a slope. Alright, so before we get into the specific numbers, let's do a free body diagram for the skier, or really any object that's really sliding down a hill. Alright, so the skier is not pushing off. The skier is just sliding or gliding down the hill. In a situation like that, let's think about the forces that are present. Alright, weight always down. Oh, and by the way guys, don't forget, on inclines and free body diagrams and everything going on with this, we tilt the X and Y axis. That was something important we talked about in the last video. The X axis is now along the incline and the Y axis is, like always, perpendicular to the X axis, therefore perpendicular to the incline. Alright, so let's start with the overall weight, which is down, right? And we refer to the angle as theta, and this is FG. Don't forget that the overall weight splits up into two components. FG perpendicular, that pushes us into the incline, and this one, let me draw a little bit better there, and this second one is FG parallel. And again, it should be drawn looking parallel to the incline. The perpendicular component here should be drawn looking perpendicular. So if you have to draw that on a test or a quiz, they should look that way. I'm not going to get a roller out and measure perfectly, but they should look that way. FG perpendicular is the part or component of the overall weight that pulls me down the incline. And remember, yesterday we made two formulas up for these two components based on the fact that the angle in this triangle is also theta, which I proved in another video yesterday. Alright, we also have the normal force pushing up on the skier that doesn't allow it to fall through, and this time the only big difference on this diagram as compared to maybe the at-rest one is friction. Since I'm sliding down the incline, remember, friction always opposes, and it opposes along the incline pointing up it, but it's kinetic friction because we're sliding. Okay, so there's all our forces, and let's make one more connection that's important with the normal force. And that was that normal force balances not with the entire weight anymore, only with what's opposite of it on the y-axis, which is just the FG perpendicular. We'll need that later, but I'll mention it now. Right? It's not equal to the weight, it's equal to the perpendicular component of the weight. Remember, not all your weight goes into the incline. Okay, so let's see what we've got and where we go. We were given the mass of this person. I'll list my givens over here, 62 kilograms. We were given that the hill is sloped at an angle of 37 degrees. The coefficient of kinetic friction between the skis and the snow, mu sub k, is 0.15. Remember, no unit on that. How fast is a skier going 5 seconds after starting from rest? So if we started from rest, we got VI equals 0. The time we're going for is 5 seconds. How fast after all that? That's VI final we want to find after 5 seconds. Remember guys, when we are started to get V's, VI's, VF's, T's, possibly D's, stuff like that, we need to use the kinematic equations at some point. We just don't have enough information yet to use the kinematic equations. That's because we have to use Newton's second law to solve for acceleration. Once we have acceleration, I could use it along with these values with the proper kinematic equation to find Vf. Alright, so the acceleration is on the tilted x-axis. So I'm going to say that F net on the x-axis equals ma. This is the a we need to solve for along the x-axis, which is the incline itself. And just be careful, anything that's along the x-axis, that means parallel to it as well. Anything that goes along the x-axis are forces we include for the F net. So what do we have? We have kinetic frictions on that axis, right? And we have Fg parallels along and parallel to that axis. So both of those are pointing along the x-axis, right? Now, here's something I'm going to do based on the fact that something I always did in the past with motion. We just happen to be on a hill now. I always make the direction we're traveling in the positive direction. So I'm going to make this positive. Downhill is going to be positive. I'm going to make this negative. All right? You don't have to do it this way, but that's what I always do because it always makes friction point negative. And since friction is always an opposing force, that usually makes the most sense. So down the incline is positive and up the negative for the reasons I just said. We have two forces on there. And when we create the formula for F net, it's Fg parallel pointing positive minus FFK pointing negative. Those are the only two forces present along or parallel to the x-axis. And that equals m times this acceleration along the x-axis we need to find. Now, we'll solve for a by dividing over m. But then we're going to have to plug in sub-formulas. And follow with me. It will all make sense, but you need to follow with me. We have a lot of substituting to do because we don't know Fg parallel, but we know a formula for it, right? So from yesterday's lesson, Fg parallel is the weight times the sine of the angle theta, but weight is mg. That was a secondary version of the formula. So all I'm doing here is plugging in a formula yesterday. I'm subbing that for Fg parallel, okay? Minus the frictional force. Well, we should remember that friction is mu, and this is kinetic friction, so it's mu k times the normal force. All this over m. But we don't have the normal force, but don't forget what I said up here when reviewing something from yesterday. Normal force is equal to the perpendicular component of the weight. That's what it balances out on that axis. So for that reason, I could sub in for normal force right here. I could sub in. I'm just going to do this one step at a time so I don't lose anybody. If you understand this after this, you don't want to show it in as many steps, but I don't want to lose anybody. So I could sub in Fg perpendicular right there. Well, that still doesn't super help me. Why? Because I don't have Fg perpendicular given, but yesterday we learned a formula for Fg perpendicular, and I'm going to sub that in. So mu k is still there, and Fg perpendicular was equal to weight, or mg, times the cosine of the angle, all over the mi divided. And now I finally have all those as givens, right? So I could finally solve for the horizontal acceleration along the incline, right? But I could do something else. If you miss this, it's not a big deal because the mass was given, but you might run into a problem where mass is not given, and if you don't do this, it'll look like you're stuck. Notice this is all divided by m. This is a term, and this is a term. Maybe some ugly terms, but they're all a term. Mass is in this term, and mass is in that term. And since it's in every term in the numerator and it's also on the bottom, it could cancel everywhere. So now I plug in the numbers. 9.8 is G, like always, times the sine of the angle, which was 37, minus mu, which was given as 0.15, u sub k, times little g, 9.8, times the cosine of 37. Make sure you are in degree mode, and carefully plug all this in to your calculator. And running those numbers, I get an acceleration of about 4.7 or 7.2, depending on how many decimal places you take it out to, meters per second squared, down the incline, because positive was actually defined as down. That's how I did it up top. All right. If you defined your direction differently, then you would have got negative 4.72 meters per second squared down the incline. But I made down positive because that's the direction I was traveling in. Just the way I like to do it. Alright, remember, that's not my final answer. My goal was to find acceleration to use with this information to actually solve for the final velocity. And that's just finishing off with third kinematic equation. Vs squared equals Vi squared plus 2 times A times D. Right? Oh, actually, I lied. I apologize. This was the wrong equation because we don't have D, we have T. So that means I've got to use the formula Vf equals Vi plus A times T. There we go. It's already solved for by nature, Vf, so we just plug in the numbers. That's 0. So it's really just A times T, which is the 4.72 that I got down here. 4.72 multiplied by 5 seconds that we accelerated at that rate for down the incline. And I get 4.5. I get about 23.6 meters per second that this skier must be traveling at. Alright, so mainly we did a lot of substituting, yes, but the main part of this problem was stuff we've done before. Use Newton's second law, identify the forces on the axis, solve for what we got to solve. There was just a lot of subbing along the way, but all that subbing is things I carefully defined and plugged in. I did everything step by step. I didn't skip anything, so hopefully everybody can follow along here. Alright, your homework is going to be on page 135, and it's going to be numbers 39, 40, and 41, as well as 44. '39 hopefully should be pretty easy to follow. It is just redoing part of the example we just did, changing the angle a little bit. As a matter of fact, we only have to refine the acceleration. So if you do like the part we did all in red on the last example, you're just redoing it. All the same numbers, only the angle changes. Number 40 should be pretty similar to the example as well. So all different numbers, similar example. Number 41, I'm going to give you a big hint for, so please listen. Alright, it's also going to refer to, so this is for a little hit for 41. It refers to the same skier in our example, but it's going to say that the snow suddenly increased and made the net force on the skier 0. What's the new coefficient of friction? So first of all, mu k is no longer 0.15. It's what we're solving for. Okay, don't make it 0.15. It's the unknown. Alright? But the big thing here is it says the net force now equals 0 because of the conditions sent forth. So we're going to set up, all the same forces are present. So when you set up the F net on the x-axis equals max, the big thing is here, if we're going at a constant velocity now, alright, that means that's how the net force would be 0. Alright? So basically the friction of the snow got to a perfect amount that didn't stop the skier, but it stopped the skier from accelerating, and he just coasted down constant. Meaning this side of the equation is going to be 0 instead of ma. But the forces involved in F net along the x-axis are still the same ones that we defined in example 6. Alright, just set them equal to 0 and solve for mu. Alright, so there's some hint to get you started on 41. But again, I will post and on the video of us going over the full solution, and it'll be a live session on Thursday, so if you have any more questions on that. Also, I want to give you a big hint on 44. Let's just set up the free body diagram together. And there's a slight twist to this one that changes a couple things. Instead of an object or a person or a thing sliding down an incline or being at rest, we can do all kind of variations. We're going to be pulled up the incline this time. Alright, so let me set up the free body diagram to start you off on this one. Alright, we would still have normal force up like this. We would still have weight down, and that weight would still break up into the two components, FG perpendicular and FG parallel. Okay, but now we're holding on to a rope pulling us up an incline, right? And the incline's 14 degrees. But this rope is pulling me like this, so we have a tension upward. Since I'm sliding up the incline, now my friction, I'm sliding so it's kinetic, friction always opposes motion. So now my friction's down the incline, right? So those are all the forces present here, and we still treat the x-axis as the incline and the y-axis perpendicular to it. So when we set up F net on the x-axis, this time I'm going to make up positive because I'm moving upward. I'm going to make the direction I'm moving in positive, opposite, so down's negative, equals MA on that axis. Then now I've got three forces on the x-axis, this one, and this one, all along the x-axis. One of them is positive, one of them is negative, so it's tension minus the parallel component. Tension's pulling me up, the parallel wants to pull me down, the parallel component of weight. The friction kinetically also opposes my upward pull, and all that equals MA times X. So that's the difference in that. That's the setup, one of the main setup equation. I would expect that you guys could handle the algebra and any substitutions from there. All right, so there's some starting hints on some of these problems to help you out.